Hey space friend! After last week's unpleasant conversation with my alien nemesis, I decided I needed to get the distress beacon up and running just in case the situation escalates. I've got the button wired up and ready to go, so now every time I hit the emergency beacon, this ship will log it to permanent memory because I definitely want to keep track of how many times I've had to call for help. So in this video, we're going to talk about how the Arduino's EEPROM works. EEPROM stands for Electrically Erasable Programmable Read-Only Memory. There's no way I was going to remember that. It's a type of non-volatile memory. Non-volatile memory is any type of memory that keeps its data even after the power is turned off. Examples of non-volatile memory are flashcards, SSDs, SD drives, and things like that. Volatile memory is like RAM. It's erased when the power is turned off. Every Arduino has a tiny section of memory built in separate from your sketches or variables. It stays there even when the power is turned off. That's what makes it perfect for counters, settings, logs, anything that you want to survive a reboot. Some practical use examples are a machine that tracks how many times it's been used, like button presses or cycles, a thermostat that remembers the last set temperature, a speaker or lamp that keeps your last used volume or brightness between uses, or a robot that saves its last position or task so you can pick up where you left off after a restart. EEPROM does have a lifespan. You can only write to each address about 100,000 times before it starts to wear out. Erasing memory, which is actually called overwriting, also counts towards each write. So if you want to wipe some of the memory, there is a way to do that, but it still counts towards your write limit. After that, it's likely to fail to store new values, corrupt data, or just get stuck at one value, often 0 or 255. When I say address, I mean each byte in EEPROM. The Arduino Uno has 1024 bytes of EEPROM. Each of these bytes is an address, so the addresses go from 0 to 1023. Some smaller devices might only have 256 bytes, so 0 to 255. The 100,000 write limit applies to each individual address, so you can write to each of these addresses 100,000 times before risking failure. Wear leveling is a technique used to spread out writes evenly across all the available EEPROM memory cells instead of writing repeatedly to the same spot. In practice, wear leveling means instead of always saving your writes to address 0, you would start by saving to address 0, and then address 1, and then address 2, and so on. Once you reach the end of your EEPROM memory, then you circle back to 0. Unlike other storage types where you might have a delete function, erasing data in EEPROM means writing a new value over the old one. To overwrite a byte, you would write a neutral value like 0 or 255 to that address. The reason 0 and 255 are considered neutral is because in binary, 0 is 8 zeros, so all bits are 0, and 255 is 8 ones, so all bits are 1. When EEPROM memory cells are freshly erased or unused, they typically start with all bits set to 1, so a value of 255. Writing data to EEPROM involves changing some bits from 1 to 0. To erase data, EEPROM needs to be reset back to all ones. On many microcontrollers like the Arduino, the EEPROM can't be truly erased without using a special erase cycle. So writing 255, or all ones, to a cell is often used as the empty or neutral marker, meaning nothing is stored here. Writing 0 means that the byte is fully written with zeros. Some people use 0 as a default or cleared value, but in raw EEPROM terms, 0 is not the erase state because erased EEPROM is all ones. If you want to check if an EEPROM cell is empty or unused, checking if it equals to 255 is usually the way to go. This is a really simple project since we're just doing an example of how memory storage works. All you need is a push button, a breadboard, and 2 jumper wires. Connect one jumper wire to pin 2 and the other 2 ground on the Arduino. First, we're including a library. This one already comes installed. You don't have to install it manually. Then we set the button pin to pin 2 and initialize an integer variable count to store how many times the button has been pressed. Last button state tracks the previous state of the button, which we're initializing to high, because we're using input pull-up. This internal pull-up resistor makes the button read high when it's not pressed. Last debounce time stores the time in milliseconds when the last valid button press was detected. This is used for debouncing because when you press a physical button, the electrical contacts inside likely don't make a simple on-off switch once. Instead, they bounce rapidly between on and off states for a short time, usually just a few milliseconds because of mechanical vibrations. If the Arduino reads the button state during this debouncing, then it might think that you press the button multiple times very quickly instead of you only pressing it once. So debouncing is the process of ignoring those extra bounces. So the program only registers one button press per actual physical press. Debounce delay sets a debounce delay of 50 milliseconds to avoid reading multiple presses from one physical press due to this button bounce. count address defines the EEPROM memory address, which we're setting at 0 to where the count variable is going to be stored. In the setup, we set the button as an input pull-up, and then we start the serial monitor. We're going to print out onto the serial monitor how many button counts we've done. This EEPROM.read section reads the previously saved count value from EEPROM address 0, so the count persists after power loss or reset. Then it prints the initial count to the serial monitor. In the loop, reading is going to read in the current state of the button, whether it's high or low. If the reading is low and the last button state is high, meaning we have now pressed it and the previous state of it was unpressed, and the milliseconds minus the last debounce time is greater than the debounce delay, then we're going to update the last debounce time to the current time and increment the button press count. We write the updated count back to EEPROM, saving it permanently. Then we print the updated count to the serial monitor and then update the last button state variable to the current reading for the next loop iteration. Now our ship's distress beacon isn't just blinking, it's remembering every SOS even if the power cuts out. Now no matter what other cosmic chaos hits us, we'll know how many times we've called for backup. Backup that we'll probably never get because I'm pretty sure it's just me and my alien nemesis floating around out here. The $100,000... What? The $100,000... Why do I keep saying that?